Chapter 2 is perhaps one of the most important chapters in this entire course. As such, we're going to go into a fair amount of detail about some of the physics behind energy and temperature. And then in subsequent videos, we will talk about heat and how our atmosphere is heated and how we retain that heat. So let's start off with this video where we will first of all define energy, at least a very loose definition because it gets a lot more complicated as deeper you get into physics. And we'll also look at what temperature is as well as the different temperature scales. Okay, so first of all, energy comes up in our lives every day. We talk about it all the time, but what is it? There is a very complicated definition to this, but the simplest definition that we can give to it is the ability or the capacity to do work on some form of matter. For example, I eat my Wheaties in the morning. I eat my breakfast. I've got energy so that when I go to the grocery store and I push the shopping cart, I use some of that energy that I have stored up and I put it into a different form of matter. In other words, I put it into the motion of the shopping cart. Okay, very loose definition, the ability or capacity to do work on some form of matter. Now, there are a few different types of energy that we consistently talk about. One is potential energy. This is the potential to do work. Think of it as stored energy. Okay, the two main potential energies we generally talk about are gravitational potential energy. If you have a big heavy weight and you lift it up high, then you have energy stored. So as soon as you let go, that energy will start moving the heavy object, back down to the ground. Okay, so potential energy is the potential to do work. And then if you lift something up high, you have the potential for gravity to be doing the work. Springs are another common example of potential energy, where you stretch out the spring, it's ready to move, it's ready to flip back as soon as you let it go. So that's another form of potential energy. The one we are more concerned about in this course is kinetic energy. Kinetic energy is the energy of motion. And the way we calculate it is we take half of the mass and multiply that by the square of the object's speed. Right? Now, here's a very interesting question. If you were to double the speed of an object, what would happen to the kinetic energy? Well, notice here that the speed is squared. So if you have a speed of 1 squared is 1, but then double the speed. Let's now have a speed of 2 squared is 4. So that means that if you double the speed, you actually quadruple the kinetic energy. Okay, very important relationship that will come up later on in the course. Now, we've got a problem here. We can measure the kinetic energy of large objects, such as a marble rolling on a table, a car on the road, an object being dropped, a bullet from a gun, any large object that's moving, we can actually measure its kinetic energy quite easily. But in this course, we're worried about the atmosphere. How do you measure the kinetic energy of the atmosphere? Especially since the atmosphere is made up of, I can't even tell you how many molecules. It's so many. Billions, trillions, quadrillions of molecules. Just tiny little molecules. How are you going to track the kinetic energy of every single molecule? Well, the way we do that is special field of physics called thermodynamics. We talk about the average kinetic energy of all of the molecules, and that average kinetic energy is indicated with temperature. Okay, so we often talk about the temperature, and we say, oh, it tells us how hot it is outside. It's way more than that. The temperature actually measures how much the molecules in the air are moving. Now, if the molecules are moving very slowly, then we're going to have low kinetic energy, so we're going to have a low temperature. The molecules in cold gases move very slowly. But if you heat it up and give it a very high temperature, then that means it's got a very high kinetic energy. The molecules are moving really, really fast. Okay, so that's what temperature is. It's a measure of the kinetic energy in the air. Now, we have three different scales to measure temperature. We have Fahrenheit, which is the one we're most used to here in the United States, Celsius, which is most used in the scientific community, and Kelvin, which is also one in the scientific community. Celsius is also the unit used in other countries as well. I should mention that as well. Where do these scales come from? Well, Fahrenheit came from, Mr. Fahrenheit. He was trying to find some scale to measure temperature. They didn't have an established temperature scale yet. He said, well, we need two good solid reference points. So he found some solution made of alcohol and salt, basically, that consistently froze at the same temperature, even under a lot of different atmospheric conditions. It consistently froze at the same temperature, and so we call that 0 Fahrenheit. Then he said, okay, I need another point, and said, well, what do we deal with on a daily basis? How about ourselves? Human body temperature, he called that 100 degrees Fahrenheit. Now, we know he was off a little bit. Human body temperature is actually 98.6, but that's pretty darn close, actually. So those were his two reference points. So he had a 0 Fahrenheit and a 100 Fahrenheit, created a scale of 100 points in between, and you've got a Fahrenheit scale. And it turned out that water froze at 32 degrees Fahrenheit and boiled at 212 degrees Fahrenheit. Okay, that's not a bad system. It's actually pretty reliable. But we don't really use this alcohol saline solution much at all in the real world. What we deal with all the time is water. And so we created the Celsius scale, which is based on water. 0 is the freezing point of water, and 100 is the boiling point of water. There is one problem to this. It's not a big problem, but it is a problem. The freezing point and the boiling point can change on a number of things. One, atmospheric pressure. If the pressure drops, then water boils at a lower temperature. If there are impurities in the water, it will freeze at one temperature. If there are fewer impurities, it'll freeze at a different temperature. So there's a little bit of variability. But we have come to establish a very clear standard, which is 0 degrees is the freezing point of water, 100 is the boiling point of water at sea level under a standard atmospheric pressure. Okay, that was a lot of explanation. You don't need to remember all those details, but I just want you to get an understanding of where these scales come from. That brings us to our third scale. The third scale is the Kelvin scale. What is this? The definition of temperature comes into play here. Remember that temperature is just a measure of the average kinetic energy of all the molecules. Well, what would happen if you could remove every little bit of energy from all of those molecules? This is purely hypothetical. We haven't actually been able to achieve this, but it's a very hypothetical situation. If you remove all the energy, then that's as low as you can go. You can't remove energy if you don't have any energy to remove. That is an absolute 0 point of energy. And so the temperature that describes that, we call that absolute 0. Absolute 0 is the temperature at which there is no energy left. And it so happens that this happens at a temperature of negative 273 degrees Celsius. That would be the temperature in Celsius, but in Kelvin, we're just going to rename that as 0. That becomes our new 0, and then we just use our Celsius scale there. So absolute 0, let me get a laser pointer here. I'm going to need it for this. There we go. Absolute 0 is negative 273 Celsius, 0 Kelvin. So 273 degrees above that, you get to the freezing point of water. Okay. And then 100 degrees above that is the boiling point of water. All right. So if you increment the temperature by 1 degree Celsius, you are also incrementing it by 1 Kelvin. They have the same size increment. Not the same with Fahrenheit though. Okay. If you do this in Fahrenheit, well, the difference between the boiling point and freezing point of water, take 100 Celsius minus 0 Celsius, it's a difference of 100 degrees Celsius. But if you look at this in Fahrenheit, the boiling point of water is 212 Fahrenheit. The freezing point is 32 Fahrenheit. That's a difference of 180 degrees. So if we take that ratio of 180 degrees over 100, that gives us a ratio of 9/5. Now, if you've done temperature conversions in the past, then this should look very familiar. In fact, here's the conversion right here. If you're given a temperature in Celsius, you can multiply it by 9/5, and that will convert it to Fahrenheit, with one problem. 0 Fahrenheit is not equal to 0 Celsius. There's a 32-degree offset. So after you convert this from Celsius to Fahrenheit, you then need to add 32 degrees to get it on the right scale. All right? So if you have a temperature in Celsius, multiply it by 9/5, then add 32. If you want to go to Fahrenheit, you do just the opposite. So you take your temperature in Fahrenheit, you get rid of that bias, so you subtract 32, and then you multiply by 5/9 instead of 9/5. Excellent. Going from Celsius to Kelvin, probably the easiest unit conversion you'll ever have. Temperature in Celsius, just add 273 and you'll be in Kelvin. That's all you need to do. If you're in Kelvin, on the other hand, you just subtract 273 and you're back in Celsius. There you go. So there will be some exercises, some practice problems on temperature, these unit conversions, as well as discussing the definitions and all of that. But as far as temperature itself, we needed to talk about it before we talk about heat. But temperature itself, we're going to hold off until we get to chapter 3. We'll talk more about it there. In the meantime, our next video, we're going to dive into our discussion on